Please pause the video before you listen to the explanation. This is an example of a matched pair experiment. We're looking at an experiment which is a treatment for melanoma, where white blood cells are genetically engineered to better recognize and destroy cancer cells. So these white blood cells are infused into patients. So we have 11 patients, so that's our sample. So n equals 11. We have 11 patients, so the sample size is 11. These 11 patients did not respond to any other treatment, so this new treatment is being experimented on them. The measure here is given in the tables, and it's the counts of active cells per 100,000 cells before and after infusion for 11 subjects. So this first row gives us the before count of active blood cells per 100,000, and the second row gives us the active cells per 100,000 cells. So what we're trying to prove is that that the treatment is effective in increasing the number of active cells. So does the treatment increase the number of active cells? So that's the question we're trying to answer. So first let's write down the statement. So clearly it's a hypothesis test. It says, is there a significant increase in the counts? So clearly we are looking at an increase, which means we need to use at some point the symbol greater than. So the question is answered by yes or no. Yes, there is an increase, or no, there is not. Either way, you'll have to provide evidence which makes it a hypothesis test. So we're doing a hypothesis test, and we'll first find evidence that there is a significant increase in the counts of active cells after the treatment. So that is the statement we have to make before we start thinking about how to solve the problem. Now that we know what question to answer, now we have to think about how to answer the question. Which problem solving method do we have to use? So we have a before and an after. Notice that it's the same set of patients so it's 11 patients. The same set of patients get the two treatments. So after getting the treatment, the active cells are, the number of active cells are measured, and before they get the treatment, there's always a number that we have to make a note of. So the same 11 patients are measured twice, one before the treatment and one after the treatment. So same person gives us two numbers, before and after. So that makes it a matched pair experiment. Same person gives us two separate measurements, so it's not a two independent sample problem. So we have just one sample, and then based on that one sample, every person in the sample is giving us two different numbers, and we tabulate those numbers in the before row and the after row. So it is clearly a matched pair experiment, and it's important to say this in formulate. Explain why it is a matched pair experiment. The same sample of 11 patients are administered two treatments, and we can think of the before measure as a treatment. So it is a matched pair problem. You not only have to say that it's a matched pair problem, but you also have to say why it is a matched pair problem. The next thing I want you to write down is the formula that you're going to use. So it's a matched pair problem. We use the single sample T procedure to do a hypothesis test using the formula x bar minus mu naught divided by S over radical n. So the T statistic, it's a T procedure, so the T statistic is given by this formula. It's important to write down the formula because that tells you what to do next. The formula tells you what numbers you need, and that's a start, and then we can start solving the problem. You need the sample mean, the sample standard deviation, the sample mean is x bar, the sample standard deviation is s. Now, before we move on, we need to think about what exactly is x here. If it is a matched pair problem, what we need to do first is create a third row which measures the difference in the after and before counts. So depending on what exactly we need to do, we need to take the difference, but do we need to go after minus before or before minus after? It really doesn't matter. If you go before minus after, you'll get negative numbers, many of them, and your average is going to be negative or less than 0. But if you go a minus b, then you get mostly positive numbers since the treatment is working based on the numbers that we see. So look at all positive numbers and mostly positive, and when you take the average of those numbers, that's going to be positive as well, greater than 0. It doesn't matter which way you go, but it's important to remember whether you're expecting positive numbers or expecting negative numbers as x bar or the mean of those differences, because based on that we'll set up a null and alternative hypothesis. So here we can assume that the counts after are greater than the counts before. So just for convenience, I'm going to go after minus before. So my x bar is going to be positive, or which is the same as greater than 0. So I take the differences. 14 minus 14 is 0. 7 minus 0 is 7. 1 minus 1 is 0. 215 minus 0 is 215. So write down all the differences. This seems to be an outlier, but for now we'll just use it. So what we've done here is created a new row, and the new row is a variable. Obviously it's going to be different for each difference. So it is a variable which goes after minus before. In a matched pair experiment, we are allowed to take the difference because each is a subject. It's the same subject. So this is subject number 1 who is giving us 2 numbers, and it is okay to take the difference. This is subject number 2 who is giving us the 2 numbers. It's okay to take the difference. So the difference can be taken in the matched pair experiment. This cannot be done in a 2 independent sample procedure. So once we take the difference, we don't need these 2 rows anymore. We can ignore this completely. All we need is the new row that we created. This is going to be used in our calculations. So our new variable x is the difference. It's the difference between the after and before. I'm saying after first because I'm going after minus before. This part is very important to understand. It's only in a matched pair experiment can you take the difference because the numbers are coming from the same subject. So our new variable is x, the difference. That's important to note. Now the variable has changed. We don't need the old 2 pieces of information or rows of information that we got. All we care about is our new variable x. We have created this new variable x, which is our difference. So now we continue with the hypothesis test, and let's look back at the formula. T equals x bar minus mu naught divided by sigma over radical n. Now we know that x bar and s are the sample mean and the sample standard deviation of our new variable x, which is the difference. So all the numbers that you need to enter into your calculator are these. Enter these numbers into your calculator to find x bar and s. Now in a hypothesis test, we need to first set up our null and alternative hypotheses. So let's see what the null and alternative hypothesis is. Again, remembering that x is the difference in the after and before counts. So after minus before is the difference x. So what we're trying to prove is that the difference a minus b, that is after minus before, is greater than 0, which means the after counts are larger than the before counts, because that's when you know that the treatment is working. So a minus b has to be greater than 0. So in other words, what we're trying to prove is that mu, the mean, the hypotheses always have the population mean, mu, is greater than 0. That's what we are trying to prove. But if we went before minus after, then that would be a less than 0. But right now, it is after minus before. So this is going to be our alternative hypothesis. Once we know what we need to prove, let's think of what the null hypothesis is. The null hypothesis always says there is no difference. If there is no difference between the after and the before, it would mean that that would be equal to, I'm sorry, that's a typo, after has to equal before if there is no difference. So that's what tells us that mu equals 0 is our null hypothesis. Now once we've carefully thought through the null and alternative hypothesis, we set up our significance level of 0.05 usually, and the rest is routine. So you find your t statistic, you find your p-value, and then complete the hypothesis test. Now we've got all the numbers in our formula. We have x bar, we have s, we have sample size n. The only thing missing is the mu naught. If you remember, mu naught is the number that comes from the null and alternative hypothesis. This number, which is the same in the null and alternative hypothesis, is the mu naught. So in this case, mu naught equals 0. Now this is a t procedure because sigma is not given. It is a t single sample t procedure. So in order to find the p-value, we need to use table C. And in order to use table C, if you remember from before, you need the degrees of freedom. Degrees of freedom is sample size minus 1. So it's n minus 1. Sample size is 11. 11 minus 1 is 10. So that is the degrees of freedom. Those are the degrees of freedom. The number of degrees of freedom is 10. Now once we have all the numbers, this is mu naught, this is s, this is n, and this is x bar. And remember that x bar and s come from the new variable x, which is the difference that we have created. So it cannot be a z procedure, it would have to be a t procedure in this case. And our t statistic is 2.16. Now that's not the end of the problem. We need to take our t statistic to the table of the t distribution, which is table C, and find the p-values with degrees of freedom 10. Now when we look at the row headed by 10, which is the degrees of freedom 10, 2.16 lies between 1.812 and 2.262, and the p-value lies between, so the p-value for 1.812 is 0.005 and the p-value for 2.262 is 0.025. But when you write down an inequality, make sure that the smaller number comes on the left, the larger number comes on the right, which tells us that the p-value lies between 0.025, the smaller number, and 0.05, the larger number. Now once we get our p-value, our last step is to compare it with our significance level 0.05. Clearly the p-value lies between 0.025 and 0.05. So it would have to be less than 0.05. So clearly we can reject the null hypothesis. So now we have to write down our formal conclusion in simple language. It all depends on what your statement of the problem was. So our statement said we need to find evidence that the new treatment significantly increases the number of active cells after increases the number of active cells. So here is how we write down our final statement. So we say we have evidence, and the minute you say evidence, write down your evidence, because without the evidence you don't have anything. So we have evidence, write it down, present it, to say that there is a significant increase. We're talking about a specific direction, so that's an increase in the number of active cells after the treatment. So just reminding you once again, if it is a greater than, which is an increase, or less than, which is a decrease, then we use a one-sided T procedure. But if it's something not specific, like a not equal to in your alternative hypothesis, then it would be a two-sided T procedure. That's how you identify what kind of procedure you need to use. Is it one-sided, which means does it go in one direction, which is less than or greater than, or is it two-sided, which means not equal to? When you say not equal to, it's not specific. It could be less than or greater than. So just like in any hypothesis test, we figured out our x. In the matched pair experiment, our new variable x is the difference, and be careful which way you're taking the difference, because that would decide whether it's a less than or greater than in your alternative hypothesis. Once you've set your null and alternative hypothesis, set your significance level, which is 0.05, calculate your t statistic in this case, find your p-value, compare it to your significance level 0.05, and make a conclusion.